Hi all, myself Nisha Verghese. I'm a PhD scholar from IIT Madras. Now I'll give a presentation on Week 0 on the subject image signal processing. So this will help you to get some knowledge, some initial knowledge about this topic, image signal processing. So the contents are, first I'll explain image formation and about resolution. Then I'll give some applications of image processing. Then how an image is represented. Then next comes image enhancements and about geometric transformations and about image mosaic. These all topics I'll cover. First is image formation. So here in the second figure you can see an image is formed on our eye. So an image formed inside a camera is similar to the image formed inside an eye. So in the case of digital camera, image sensor consists of a number of arrays known as pixels. So each pixel will have a certain density inside that pixel. So here you can see one image where the image plane is divided into different pixels, and at each pixel the intensity is the same. So let us consider an image like this. Here for the first image we have only two colors, black and white. How many pixels are there in the first image? Here we have 1, 2, 3, 4, 5, 6, 6 by 6, 36 pixels are there in this image, and we have only two colors to represent this image. So for black we can use 0, pixel value 0, and for white we can use a pixel value 1. So we have to use 1 bit for 1 pixel, 0 for black and 1 for white. Here we have 36 pixels, so for each pixel we have to use 1 bit. So total we have to use 36 bits to store this image. Let us consider the second case. Here this image has 4 colors, one black, white and one dark grey and one light grey. So we have 4 colors to represent this image. Here, similar to the previous case, we have 36 pixels, but here we have to represent 4 colors. In order to represent 4 colors, we may have to use 2 bits. 0, 0 for black, 0, 1 for this dark grey, 1, 0 for this light grey and 1, 1 for white. So we have to use 2 bits per pixel. Since we have 36 pixels, we have to use 36 by into 2 is equal to 72 bits to represent this image. So as we increase the number of intensities, number of colors, gray colors, we have to use more number of bits to represent this particular image. So next we are going to the topic resolution. There are two types of resolutions, spatial resolution and gray level resolution. Spatial resolution means this image, as you can see, number of pixels for a particular area is less. But here for this image, for the second image, number of pixels in a particular area is more. But for the third image, number of pixels for this particular area is very large. So this indicates that as the number of pixels in a unit area is increased, it will increase the spatial resolution and it will increase the quality of the image. So if you want to get more clarity, we have to increase the spatial resolution. So we have to increase the number of pixels per unit area. Then comes gray level resolution. Spatial resolution relates to the number of pixels, but gray level resolution relates to number of gray levels we are using. As in the previous slide, I have explained the second image. We used 4 intensity values: black, white, dark gray and light gray. So here we have 4 colors like that. The first image has 256 gray levels. But the case is that we may have to use more number of bits to store this image as we increase the number of gray levels. For the third picture, we are using only 4 gray levels. So the quality of the image is reduced as we reduce the gray level. So as we increase the gray level resolution, as we increase the number of gray colors in an image, the image quality will be increased. Then comes some applications of image processing. So this thing will be already discussed in the videos. So I'll just give some snapshots of different applications, that's all. The first slide gives some consumer camera application. First one is autofocusing. As explained in the video, some image processing is also there for autofocusing. Then comes HDR imaging. Here in the first picture, you can see some of the images are actually black in color, so we can't see any portion there. But after HDR conversion, we can see those portions. So here also some of the portions are oversaturated. So after HDR processing, we can see those portions. So this is what is meant by HDR imaging. I'm not going into detail, but I'm just giving some output and input images, that's all. So next comes low light photography. So here we have to deal with photo noise and all. Next comes motion deblurring. Here, due to the motion of the camera or motion of the object, we may have some motion blur in a particular image. So that we have to deal with, and we have to deblur those blurred images. So that is motion deblurring. Then comes image mosaicing. Image mosaicing is connecting different pieces of images to get a high field of view. So you can't simply stitch them, but we have to use some transformation center. So this is image mosaicing. Then image sharpening, that you have already known. Then comes robotics. In robotics, depth, we have to find out depth map. Depth map is from a monocular image, from one image. So here you can see this portion is actually far from this camera. So that portion will be given red color, and the nearby portions will be given blue color. So this is the depth map from this image. So this thing we have to find out from a single image, and from two images, from stereo images, we have to find depth. So this is also another application. Then for biometric, we have to identify some person from the biometry. So this is one of the applications. And for surveillance, some object detection and tracking algorithm should be developed. Then motion deblurring also is there for surveillance. Then come astronomical imaging. Here we have blurred image, and those images will be deblurred here. And for medical imaging also, image processing has very much application to diagnose some diseases. Then underwater imaging enhancement is another area. So this is a representation of a particular image. So there are actually two types of images, grayscale image and RGB image. For grayscale image, we have only one plane, and that one plane will be saved in the code as a matrix. So say this is an 8-bit image. 8-bit image means one pixel is represented using 8 bits. 8-bit means we can have 256 gray levels here. Because as in the previous case, if we have only 2 bits to represent one pixel, we may have 2 raised to 4 gray colors in the image. Like that, if we are using 8-bit image, we will have 2 raised to 8, 256 colors in the image. Colors is gray colors. So the colors will be represented using 0 to 255. Then that matrix will be saved as a, so this image will be saved as a matrix with size W process. W is the width of the image and which is the height of the image. In the case of RGB image, one RGB image is represented using 3 channels, red, green and blue, and each plane will have W by H dimension. So the whole image will be represented using W by H by 3. So this is the difference between grayscale and RGB image. And these are some geometric transformation. These topics are already covered in the week 1 session. So here translation is xt, yt, xs, ys are the target positions, pixel positions and source pixel position. So we have this much translation from the source position. Translation is a translation from a particular position to another position. That's all. And rotation is inclined rotation is given here. Here the rotation angle is theta. So by multiplying x's y's with this rotation matrix, we'll get the target matrix. Then scaling is actually here we are using this matrix for scaling A0 0B for scaling output is like this. So the whole geometric transformation can be represented using a single matrix multiplication H that is given here. And there are other transformations also other than this translation, rotation and scaling. So I just mentioned the names only: affine transformation, symplectic transformation, projective transformation, etc. So those all transformation can be represented generally using this H matrix. So these are some examples here. This is original image, and this is a similarity transformation, and this is an affine transformation, and it is a projective transformation. So in normal images we can see some projective transformation here. So that can be converted back to the original one like this. So there we are using this H matrix. Then comes some image mosaicing example. Here we have 5 parts of the same scene, and we have to club all of them. So we have to find out some transformation between every pair of images, and using that transformation we stitch those images like this. So this is one mosaicing example. Here stitching is done using 5 images. So that's all about the introduction part. Then comes programming assignment part. So Colab is a platform that can be done in browser itself, where we can run Python codes freely. So in order to start Google Colab, just type Google Colab. Then the first link itself, just type there. And if you are not logged in, just log in using your mail ID. So some window will come like this. Then file, new notebook. So here in this window, some tab will be open. Here you can type your code like this. Something like that. We can write the code, and again next tab we can open like this. Any text tab we can open like this. Yes, I have already copied some code here. So this is the code I wrote. So here first of all we have to import some already available libraries that can be used for some manipulations and all. So NumPy and Pandas are array manipulation and data manipulation libraries. So they are imported here. Then CB2 is the library used for computation tasks. So that is also imported here, and SkyImage and Matplot libraries are also very much useful libraries for image processing tasks. So those required libraries we have to import here in the first tab itself. Then here I have written some code to get some array. Array is a matrix 1, 2, 3, 4, 5, 6. So that is read here and it is printed here. So print option will print it like this. Okay, then this is one function print. So here uh, some element is extracted. Which element is extracted here? Actually, in Python, the element starts from 0, 0. So it extracts element 1, 2. That means the second row. 0 indicates first row. So 1 indicates second row and 2 indicates third column. So it extracts the second row and third column element, that is 6. Then in the next line it extracts all the rows and third column. So all the rows and third column, that is 3, 6. Then comes the second row and 1 to 2 to 3 column. So second row and 2 to third column. So that is 5, 6. That is printed here. So these all are very simple examples that you can try with. There are examples, introduction codes are there in Colab itself. Here itself, some examples are already given that you can go through. Then I'm just reading one image, some kit.jpg image here, and so this kit.jpg image we can export here. So here, so I'll export this one. This kit element is already there on my laptop. So I just upload that kit.jpg element, that picture, and I just read it using CV library here, and I just show the image using CV2 IM show. Then I just printed its shape. Okay, so this is the image. So I just run the code. Here I'll just run the code. You can make it. I have to run from the beginning. Here I ran the code. Okay, then here I'll run. Okay, I ran the code. So the image will be displayed, and its size is also displayed. 1200 pixels, 1200 pixels by 3. 3 is for red, green, and blue. Then we have then here I am doing resizing to 400 by 240 pixels. So, and I am again displaying it here. So I resize to a lesser size. Then the next one is I just blurred the image using some kernel. So some blur kernel I am using. So these things you will study in your course. So this is a blurred image, and some other filter I have used for sharpening also. So that is showed here. So here it is a sharpened version. This is a blurred version. Then comes I am converting that color image to gray color. So here the output is here, and next comes I am doing the negative process, inverse process. So I'll get the negative of this image. Then I'm just reducing the intensity value, -50 I'm doing. So brightness will be reduced here, and +50 will increase the brightness. So next is I'm increasing and decreasing the contrast by multiplying with a number. So here the first picture is the normal one, the second picture is with lesser contrast, and here third picture is with higher contrast. So and in Python normally the images will be saved as in BGR format. So here from one URL we are extracting the image to this image. Then if that is displayed here, that will be in the format of BGR, blue, green and red. By default in Python OpenCV, the image will be saved as BGR format. If we have to convert that to RGB, we have to use this function CVT convert, and after that that image, if we are displaying that image, that will be given in the normal RGB format. So this is one of the difference between MATLAB and OpenCV in Python. Okay, so these are some introduction of this Google Colab. You can try with your own examples in Google Colab. That will help you for your assignments. Okay, that's all about this week 0 presentation. Thank you.